edition of the Heat Treat podcast. Today we're going to talk about additive manufacturing, 3D printing, or advanced manufacturing, additive manufacturing, however you want to call it. Today we have two young guests. I'm assuming you guys are my millennials, right?
I guess so.
No offense, no offense, but you know, there are very eager material engineers from Burlock Technologies. We got Tallon and Erick Tenuta, material engineers. So I gotta tell you, you will be like the youngest guest that we ever had. So super excited to talk about additive manufacturing, this disruptive process on the industry. And you know, before the podcast, we were briefly talking, and these guys seem to be very knowledgeable of the industry, very eager. And these guys are the new generation who, in a couple of years, are going to lead the industry, right? So it's super excited to be talking to young guys that are passionate about what they do. And additive manufacturing is a very trendy topic, very disruptive topic, and not many guys know it very deeply. They know the trends, they know the head titles. But let's use this podcast today to give the audience, which are very experienced heat treaters, a very new view and explanation of what additive manufacturing or 3D printing is. So first of all, how are you, Paul? How are you, Erick? You just could give us an introduction of the company you work for, which is Burlock Technologies. Where is it located? What's their mission? What's their market? What you are trying to achieve? And of course, a little background of yourselves. Both of you are in material science. You're very young and eager. So why don't we start like that? Who wants to take the lead?
Sure thing. You want me to
go ahead?
All right. Well, thank you so much for having us on. I'm very excited for this conversation and looking forward to see where it goes. My name is Paul, like you said. I'm an engineer here at Burlock Technologies. So we're primarily an additive manufacturing company specializing in metals, aluminum, titanium, high nickel alloys, steels, these kind of things. And our main customers are aerospace and space, yet we do have customers ranging in energy and automotive, etc., which is pretty great. Myself, I'm a materials engineer, like you said. I finished my master's a couple years ago in powder metallurgy, which then led me into press and sinter metallurgy more so, and then moving into additive manufacturing, which in terms of being a metallurgist, the kind of microstructures and properties we see every day is exciting, and we're kind of trailblazing in a way. So for me, I learn something new every day, which is really great. I'll let Erick explain.
Yeah, and thank you for the introduction as well. My name is Erick Tenuta. I also finished my master's recently in collaboration with Oak Ridge National Lab in additive manufacturing. And I started at Burlock here around a year ago, maybe a year and a half ago. We're located in Southern Ontario in Canada.
Nice.
And yeah, like Paul said, it's mostly space and aerospace. Our two main materials are aluminum and titanium. The vision of Burlock Technologies, which is a subsidiary of Samuel Son & Co., which is quite a large company here in Canada and in the US, is to take additive manufacturing to the level beyond prototyping, so the level to scalable manufacturing. It's not uncommon nowadays to have a university or a company with a 3D printer and people working on it very manually, which is great because obviously people can create amazing things. But the goal is to take it, like I said, to the next level, building a manufacturing process that includes rigorous quality, machining for whatever tight tolerances that parts may need, and obviously heat treatment. Because while properties out of the printer may be acceptable to some degree, they're not necessarily robust in the way that aerospace and space customers are looking for. So the goal of Burlock Technologies is to combine all of these things into one manufacturing solution.
So let's talk, we have always heard about 3D printing, and every university has right now a 3D printer. Is like a must. But just tell us the basic to people who haven't seen a printer themselves or played with a printer itself. Give us a one-on-one of the 3D printing process.
Sure. You want to start with the print and I can do the post process?
Sure. Yeah, so the basics of 3D printing isn't necessarily new. It's essentially small scale repeated welding, right? It's the most common form of 3D printing that is out there and that we do here at Burloak is powder bed fusion 3D printing. The basics are relatively straightforward. There's a layer of powder. The metal powder, which is spherical powder, is in the range of 15 microns to 60 microns in diameter. This powder is spread over an area. The layer of the powder is maybe 30 to 60 microns, depending on the printer. And then there's a fiber laser that melts layer by layer the geometry that you're looking for. So the part is built up of subsequent 30 to 60 micron layers until the entire part is completely solidified. The closest thing that is that you can relate it to is welding on top of each other, many welded sections. The range of sizes for 3D printing can range from, like I said, the 30 micron layer to literally, wire arc welding, which is not the same technology, but it's a wide range of size scales. Here at Burloak, we do mostly laser powder bed fusion. And then the idea is that at the end of it, you have this part that is only made up of material in the specific areas that you want the material applied. You can kind of think of it as the reverse of subtractive manufacturing, traditional machining, CNC machining or turning, where you start off with a large volume and you remove material. In this case, you start off the opposite. You start off with a very small volume and you build up subsequent layers to make the part.
Perfect.
That's why it's less wasteful material, because you're not taking material away. I mean, you're just adding material to where it goes.
Exactly. You only add material mostly to where you need it, and then all the excess you can recycle it. We read many times, and we constantly all assurance methods with additive manufacturing and a manufacturing scale is recycling the powder, testing the powder, making sure that mobility, the composition, and the size is usable again for the next print.
Okay.
Can I talk about the post processing?
Yeah, sure. So to be able to support that kind of manufacturing, like Eric was saying, there needs to be a lot of these different post processes and supports. So, for example, the powder itself, if we're going to recycle it, we have to test it. So we have our own testing laboratory here, where we can do most of the powder tests that are required for our directly correlated to the certificate at which the powder comes in. And so that's one way the lab supports the print. Once it is printed, there then needs to be subtractive and heat treatment to give the specific tolerance to the part that the customer requires, which we can go into after. But I think your first question was just the print itself. So
yeah, well, it actually answered about like a layer welding, right? And but one question: we actually cast apart our machine apart, or we 3D print apart. We get a part that still need to have some post machining because there might be some scale. Is it the same case with 3D printing? I mean, I see a couple of parts and you print a part, but it's not the surface is still a little rough, and you need to do post machine. Do you post machine these parts?
So it all depends on the final state at which needs to be. So a customer may have a surface finish requirement in specific areas of the part, and that would require machining. Now, the goal is to basically minimize as much of the post-processing as possible. So if a customer just has tolerance on a thread and nowhere else, and we can prove the mechanical properties of the as finished surface, then we'll just machine the threads, and it should be acceptable.
Fantastic. Now let's go to the fun part, right? Because this is the Heat Treat podcast.
Yeah,
and,
that's right.
And it's not the additive manufacturing podcast. It's the Heat Treat podcast, right? And when we heat treat steel, we're looking for surface hardness, core hardness, wear resistance, right? Stress relief, right? Now we got a 3D print part, but we might need some surface hardness in specific points. We might need some wear resistance on the part if it's a gear, for example, or some hardness. We need to make the material resistant. We got this 3D print part. Then how do we give this this hardness or this wear resistance, or let's say stress relief into the material? That's where additive manufacturing and heat treat, they intersect.
That's right. And absolutely. So there needs to be a certain heat treatment for our specific alloys to reach the properties that the customer requires. So there needs to be heat treatment for most of these parts. And so there's two parts kind of to what the question entails. One is the testing. How do we actually test the part? Because it's not traditional manufacturing where we're making a million parts. So we're not just going to take one off the line and test it. And the second is, okay, what is the actual heat treatments? So to answer the first question, each print is technically a heat. So if you're going to make a bunch of material, let's say a cast, it will be one specific heat, and that heat will have its properties. Now, every time we print, we're technically melting the powder and turning a liquid back into a solid. So it's a new heat. So in that mindset, there must be a certain amount of information we have to get for that heat. And instead of destroying the part we just made to then to test its properties, which we can't deliver, we print coupons and beside the part, or representations of maybe sections of the part for further processing. So then these coupons will go through the heat treatment and will represent the part's properties. So a lot of alloys will come out of a printer. They might be stressed out, so they'll require a stress relief so they don't, let's say, warp after getting cut off the build plate. Or if we're looking for, you brought up steels, if we need to solutionize and quench and temper, we can do that as well. Especially here, like I said, it's if you think of it like a heat, a lot of our standardization, like AMS specifications for aerospace, let's say, we kind of fall into the casting realm. So because of that, a lot of our customers require a hot isostatic press, which we have also on site, which is pretty amazing for us in terms of research and development. Having our own HIP is pretty exciting.
Fantastic. Actually, just want to make something. We do have a how does isostatic press, a podcast, very interesting. If you want to go and check it out, it's
cool.
we have chat on that one. Okay.
Oh, I'm gonna have to check that out. That sounds really great. I'm definitely interested. It's been a new technology for me to learn, and it's definitely a rabbit hole of stuff like of trying to understand it. You can just keep going. So I definitely know that I don't know a lot, but I'm learning a lot, which is cool. So anyway, these post-processing heat treatments is how we, like you said, give our mechanical properties, and it needs to be married with the print. Now, traditional casting, you're starting with the microstructure that's very large and equiaxed. And after a print, the microstructure is very fine. It's dependent on the laser parameters, and which is a small spot size compared to a cast. So even though a lot of our customers ask us for traditional heat treatment processes for a cast, which is fine, and we can get the mechanical properties that they're looking for.
Are you talking about like annealing or normalizing?
Yeah, you could, let's say, an anneal, or if you have like a high nickel alloy, there's like these very long heat treatments that have been generationed in on these casting materials, which absolutely makes sense, and they're proven and trusted. Now, in terms of additive manufacturing, since the microstructure is different right after the print than a cast, the following heat treatments don't necessarily need to be what has been generationed in. So a big part of our jobs is trying to find, okay, what is a potential heat treatment that can now give properties that have yet to be seen for this alloy? And that's kind of where our life gets really exciting, right? Mm-hmm.
It is. Well, thanks for that. But you just want to, so the statement that you're saying, because, the perception is that additive manufacturing is going to take away heat treatment. That's not correct. What Paul is telling us is actually that additive manufacturing will require some type of heat treatment.
Oh, yeah.
Is that the first statement? Is that the first statement?
Yes. Absolutely. If a customer has specific properties we need to meet, there needs to be some sort of heat treatment. And even if they don't, and there's a geometry that is such that it might warp after cutting up.
Sure.
At least that needs a stress relief. And it's if they're not married, then there can't be any improvement in the alloy itself. No, they need to be together.
And let me put it in a slightly different way to explain why we think that there will always need to be heat treatment. If you think about the process of additive manufacturing, it's thousands and thousands of layers of these welds, right? And as we know in traditional welding, even though it's only maybe the weld bead is maybe 1 or 3 millimeters wide or something like that, the stress in between the two parts where the weld meets is relatively high. Sometimes you need to preheat the welded or the pre-welded areas in order to make sure that the two, I don't know, whatever beams don't warp or something like that, right? In additive manufacturing, it's that to the next level where within one section, there will be thousands of remelted layers, right? And these remelted layers are, each one is essentially quenching, right? The cooling rate of these welds are enormous. And this produces a lot of stress inside of some of these parts, especially with something like titanium, right? So with titanium, when it comes out of the printer, is it possible that the customer will accept the as printed, no heat treatment state? It's unlikely because it's most likely not going to be as reliable as something that is stress relieved or normalized or something like that. So there is a huge need for these potentially very stressed out parts to be relaxed and possibly in this case of something like nickel alloys to be aged, right? To get to a type of mechanical property that we're used to. Eventually, what will most likely happen is when additive manufacturing matures and we move away from the traditional materials that we're used to, you know, nickel 718 or Inconel 718, Ti-64, that kind of stuff. The next phase of additive manufacturing is going to be new alloys we haven't seen, right? Things that are not so common. And then that is going to require some other new heat treatment innovation, right? So it's at the level of academia, is heat treating necessary? I mean, it depends on whatever they're researching. In industry, absolutely, it is one of the most important parts for sure.
Now, you mentioned something very interesting. It's when additive manufacturing matures, right? The maturing stage. It's well known that additive manufacturing or 3D printing is not new. You know, the technology has been there for many years, maybe decades. But what are like some products that are already here in today's world, right? You mentioned about planes. You mentioned about some cars. Some I believe you said mining, which the other industry you serve.
Aerospace, space.
Space, of course. But you know, is there like a product on or everyday's life that is actually out there made of additive manufacturing that it's very common, or not yet?
There's some that we've quoted for smaller parts. For example, what was it? It was like a bow or something. It was the trigger on a bow made out of steels. Yeah, totally. So there are some items out there that now that's not something that we ended up doing, but the industries are starting to look into it. So because if you have a build volume and you can produce, let's say, these small parts, you can make a lot of them at once. And so that I know there's some industries that are maybe more your question is like pedestrian contact, right? It's like these big industries and companies,
right? Pedestrian contract.
It's like every day someone's grabbing it. So
civilians, right?
Yeah.
one example I can think of, which Burloak does not do, but something I believe is Invisalign, actually. And those plastic braces, like the clear braces,
got it.
I believe are actually almost all of them are 3D printed.
Really?
They're made out of some kind of clear plastic or something like that. It doesn't have anything to do with heat treatment, but if you're looking for pedestrian examples.
I just want to give you examples of additive manufacturing or daily lives, right?
One of the examples that I guess people interact with indirectly is satellites, right?
Okay.
And our biggest area at the moment is satellites, and specifically waveguides, which are almost exclusively made out of aluminum. There are some titanium satellite components, which are brackets, and we currently have waveguides in space right now. So we work with a few satellite manufacturers, and these waveguides are out there and receiving signals and doing whatever research that these companies do.
And I guess just to get a little bit of how people interact with that waveguide or the satellite component, if you're going to text or call somebody, your cell phone has to go to a tower, and the tower sends it up into space. And someone might think, oh, like, why? There's so much going out into space. How does that satellite pick up my phone call and send it down to my grandma? Well, the ear on that satellite is made specifically to size, so it can hear your cell phone. And if it's bigger or smaller, that wavelength won't fit in. So if it's the right size, your cell phone signal will go in, and then it'll come back out and shoot down to planet Earth. So that's something that we are in production right now. And yeah, you're right. There is a satellite up in space with some of our parts on it. It's pretty sweet.
Cool. That's very cool to know. You know, additive manufacturing. You know, we know that it's going to be like the space, space travel thing, right? For spares and something, because you can actually print it on space, like on the International Space Station.
There's some cool research for that.
It is, I've seen a lot of movies and read a lot of sci-fi, and they actually print their spare parts. But let's go back to Earth and talk about heat treatment, right?
Yeah, nice.
Okay, automotive, right, which is like a big thing, high volume, right, made of steel. You talk about titanium, but when we talk about regular steel like 4140 and those type of steel that are used on our daily lives, right? How do you see additive manufacturing in high volume? I mean, we got castings, we got forging, we got powder metal, which is kind of what we're doing here. But do you see maybe a future which we actually switch our manufacturing way, the massive castings for very heavy stuff, or high volume for forging for automotive parts, let's say? Do you see changing it to additive manufacturing?
Yeah, go for it.
So in one of the misconceptions about additive manufacturing is replacement of existing components using additive manufacturing. If we're making like this mug or something like that, right? If there's already a manufacturing method in place that makes millions of these extruded tubes, something like that, or punched stainless steel, whatever components, there isn't really an economic or manufacturing momentum to push it towards additive manufacturing, right? The benefit of additive manufacturing comes in terms of new designs that would be, lighter weight, stronger, more ergonomic, whatever it may be. So existing components that work well, if it ain't broke, don't fix it kind of thing, is very much how specifically automotive looks at additive manufacturing. On the flip side, at the moment, while eventually it will come to the point where additive manufacturing, the cost of these printers goes down, and where companies are able to purchase more printers at a much lower cost, eventually I think that will be the case. At the moment, though, there are companies. There's a company in Ontario here called Exco Engineering, and they do instead of printing the components, they print the molds that are going to be making the components, and they print those molds using 316 or something like that, right?
M13
or MS1, which is like a miraging steel, right? And the benefit to that is you can print the molds, which we've done a few of actually here as well.
Yeah.
You can print the molds with conformal cooling channels or something like that. You can create molds like molded prototypes, right? So one of the things in mold making and die making is it's extremely difficult and takes a very, very long time. If you can print the prototypes for the molds to make 1 million parts, now we're flying, right? Now the cost or the benefit of additive manufacturing can be realized kind of indirectly, not necessarily making the punched components, but making the punches for the components, if that makes sense, right?
Yeah, that makes sense. That makes total sense. Total sense.
Yeah,
It is perceived that and maybe this is just a taboo or something, but just so just clear me out that additive manufacturing is slow because you have to print a bunch of layers. It is perceived. Don't get mad at me. It's perceived. That's why, that's why we're having this podcast, to give information to the audience. Right? It is perceived that it's a slow manufacturing process and an expensive process, right? Can you change that perception without getting mad at me, please? Right?
Yeah, absolutely.
I'm sorry, because you just did like this. You just nodded like
no.
So once again, it depends, right? If someone comes to us and says, oh, we want to print an extruded aluminum tube. Okay, yeah, well, it doesn't make sense to create that using additive manufacturing. It's in that case, you're right, it would be expensive and it would be slow. The benefit of additive manufacturing, and where it becomes very fast and very economical, is components that would consider many manufacturing processes to make one component. So as an example, I'm not sure how much of the podcast is going to be visual, but here we have a waveguide, right? And the waveguide is kind of an S shape. It's got like nice curves or something like that, right? In a traditional manufacturing process, this would be made out of 1, 2, 3, 4, 5, 6, 7 different sections, each of them with nuts and bolts, where someone would have to assemble the waveguide, make sure that each of the mating features is machined. Each of those machined features matches up with the other mating features, and that adds time, right? So while the printing process itself, it may take longer to produce this one part than the 7 individual parts, that specific making of the component might take longer, sure. The manufacturing process from start to finish is far more consolidated, right? You need less manual interference between the different components. You need less sourcing of different, nuts, bolts, fasteners, whatever it may be, right? So now you have a consolidated manufacturing process to make the same part that actually is probably more efficient than the traditional way, right? So this is where you would have to you can redesign your component to make it more efficient and a shorter time scale. So I hope that kind of gives the
it does
in terms of what is shorter.
You have to design the part, taking into consideration the pre and post processes and how much labor is gonna run. So, this kind of answers my next question, which are the limitations for additive manufacturing?
I've
been talking a lot.
No, hey, it's great. You're talking very well.
And he's getting mad at me, so you don't.
No. So some of the limitations at the moment are, since it's a kind of a new industrial method, the post-processing methods are also being developed for our specific processes. So, for example, you mentioned surface roughness. Some printers might have a specific surface roughness that is not what the customer wants, and there might be internal channels with that as well. So what are the methodologies there that can improve the surface finish? And actually, this is something that Eric knows more about. So maybe I'll let you take on that one, and then I'll
sure
to the next one. Sorry.
No, yeah, there's surface finish is definitely one of the things that many of our customers are interested in, and the surface finish of as printed materials is rough, right? For those who are interested, it can range from 100 micro-inch to, depending on the process and the printer, 1,000 micro-inch. It's a big range. Usually it's between 100 and 500, something like that. The limitations is that it does take time to post-process these surfaces afterwards. And at the moment, with all these crazy internal conforming cooling channels and that kind of stuff, some of these surface finishing techniques that are traditionally used, such as vibratory finishing or various chemical finishing, may not be applicable, and that's something that is being worked on by a variety of different companies. Different businesses are popping up saying, "Oh, these are different types of surface finishing that can apply to additive manufacturing."
Another one as well. Come on.
Sorry?
I have another one as well.
Oh, what is it?
Since we are on the heat treatment podcast, with respect to heat treatments, there's some, let's say, aluminum alloys that need to be water quenched, such that to properly solutionize, quench, and then age. Now, if we're making a near net shaped part, I mean, this is something that the press and sinter industry also has issues with. How do you properly quench something and not deform in a media such as liquid or even oil? An oil quench can do the same thing.
So we're talking about distortion right now.
Yeah, exactly. Right. Distortion. So if you've printed something and it's in its perfect shape already, and then you need to shape it
with very thin walls.
Oh yeah, also with very thin walls, and then you need to quench it, and the shape is definitely going to distort. So we need to look into methodologies where you can maybe a gas quench, and some of these aluminum alloys, gas quench is just not good enough. And so we're doing some research into that, and as well as some new alloys, because these traditional cast methods, the water quench, as an example, it works very well because you have a big cast structure that you're going to machine anyway. So that's another limitation, but it's hard to say limitation because it opens up a window for new alloys. So it's a need for something like that that can be doesn't need to be water quenched, and that's something a lot of people are actually working on at the moment.
Yeah, specifically the one of the most popular aluminum alloy is aluminum silicon 10mg, which is a very common casting alloy that is printed. The reason it's printed often is because it's very easily weldable, right? It's it prints very, very nicely. The properties are decent, and at the beginning of the kind of the industrial usage of additive manufacturing, everyone wanted the T6 condition for aluminum silicon 10mg, which is what Paul was just referring to in terms of losing its shape. And so we're working with a variety of companies, some from Canada, some from the US, about new alloys. And so these are not alloys taken from industry applied to additive manufacturing. These are new alloys specifically for additive manufacturing. And these alloys are going to have constituents that are not maybe found in traditional aluminum alloys. And that's going to involve a new development of heat treatment.
That's right.
It might involve HIP. It might involve, hopefully not involve water quenching. Yeah. That's kind of the goal, to avoid the deformation after quenching. So
yeah, absolutely. And even with let's say aluminum silicon 10mg or some new alloys, there's going to be a homogenization step. The traditional way of doing it is on these cast structures that has this very large, acryax grain structure. So the individual alloy elements need to move very far for it to be homogenized. Now, our printed structure is so fine that we should question the fact that this homogenization step is maybe 6 hours. Like, maybe it doesn't have to be. There still needs to be that step. So we're not leaving out heat treatment, but maybe it doesn't have to be as long. And so these are some questions, and we're limited by
quality heat treatment instead of quantity heat treatment.
Exactly. There, I love that. On the nose. I love it.
Guys, it's been fantastic to talk about additive manufacturing. Before we go to the end of the show, did we miss something or something else that you would like to add, just to give our audience a wider view of additive manufacturing? I believe we covered a bunch of stuff, very interesting. I learned myself a lot, and I did learn, Eric, that it's not slow or expensive if you apply it the way it should be, right? But do you want to add something else to the technical conversation?
I think we hit most of it. I guess as more of a summary of what we talked about, there really needs to be a marriage of the 3D printing. It's another manufacturing method, like subtractive. It's another tool in your tool belt. So you have to do everything. You have to be able to do subtractive. You have to be able to do heat treatment properly, and all these things for it to be successful. And just as you'd have a forging shop where you'd have a forger doing one thing at a time, we have a printer that's doing that one thing at a time. And so with multiple printers, you can get to serialized production of producing lots of parts, and then you can just push them through heat treatment and get them all heat treated together, and so on and so forth. So it's all growing in at the moment, which is very exciting for us.
And being like relatively new to the I'll say industry in general, because both of us, we just finished our masters maybe I think you were like 2.5 years ago. I was like a year and a half ago. It's awesome to be in additive manufacturing, considering that everything is new. There's always new stuff. There's always new companies popping up doing cool things. You know, as obviously we want to promote Burloak technologies, but it's great to have new competition in the field to see what other companies are doing and innovating. But one of the things that, you know, I got to plug Burloak here. One of the things that Burloak has is some really great heat treatment equipment that pushes additive manufacturing to the next step. One of which is the hot isostatic press that we have with Quintus.
Yep, that's right.
And we're doing a bunch of research on how to leverage that with additive manufacturing. And it's a great, it really is a really interesting atmosphere to be, okay, we have working with companies that are developing new alloys. And then that company says, well, how do we involve HIP? How do we involve the least number of heat treatment steps? Because, you know, we want it to be fast and agile and all this kind of stuff, right? So how do we take all these different elements? How do we take what, you know, kids have learned in their undergraduate, which is relatively new to additive as well? How do we like marriage all of these things, and how do we make a manufacturing process? It's a really dynamic atmosphere that I cannot suggest more to people looking to get into engineering. There's every kind of engineer that you can engineering major that you can get into can fit into additive somewhere, and it's awesome.
Yeah.
Nice. Guys, thank you so much. At the very end of each podcast, we always talk to elder engineers, right? And I actually asked them, what would be, some advice or personal experience that you would like to share with the new generation of heat treaters? Now, we're going to make it backwards. You know, you're young engineers with a master's in material science. You're very passionate about the industry. You talk very technical about, you know, alloys and steel types and processes. What would be an advice that you will give to the old generation of heat treaters now? I mean, I am pretty sure you interact with guys that have done the same thing for 40 years. And now you coming here and questioning that and, you know, trying to find new ways that are not proven yet, right? That may be a challenge. What would you tell to the old generation of heat treaters on that you have found useful for the company? I don't know who wants to start.
Yeah, I will. So thanks, great question. I mean, I'll do my best to answer, just because I know one of the great things about being here is that I know nothing, and that is the best way to go into a situation for me, is to like, okay, how am I going to learn about this? I think that's one thing that I never want to lose. So for example, we just went through our NADCAP accreditation process, and we got our NADCAP accreditation for our HIP, our vacuum furnace, and we got some air furnaces as well. And for aluminum, titanium, not that we can't do steels, but it's mainly on these annealed kind of alloys. But going into that, I mean, NADCAP for heat treatment is one of the, I'd say, hardest NADCAPs to do, as well as like well established. So I interacted with a lot of people who are very experienced in the industry. And one thing that I noticed in a lot of these conversations is that when they were open to seeing new processes, it was a lot easier to explain a process. And we were very fortunate. We had a very good auditor who has seen a lot, but was very excited to see, oh, like, how are you doing this if it's printed? And because of that, it was such a successful audit. So I'd say my one piece of advice to anyone who's been in industry a long time is to be open to these new processes and try to apply what you know so well to something new. And not only will you grow, but the process itself will grow. For example, even our heat treatment shop, we have an incredible amount of experience of a specific individual who's been in industry for a long time and knows so much. And there's no way that we could have done what we did without him and his knowledge and applying it to our process. And so his openness was able to produce what we now have as a state-of-the-art, high-class heat treatment shop that can do stuff for aerospace. It's pretty exciting.
Thanks so much for sharing that, Paul.
Yeah.
Anything you would like to share, Eric?
No, I honestly think Paul hit it on the head. We've been working together quite a bit, and his experience has been very similar to mine, and so I don't think I got much to add. That's great.
Well, thanks so much, Paul Tallon and Erick Tenuta from Burlock Technologies. It's been fantastic to talk about additive manufacturing. Thank you so much. Just would like to run the audience that we're loaded monthly heat treat podcasts with guys like this that know their stuff on any industries, products, reviews, processes. Do me a favor, guys. Go like this. Give us a like. Click below. Please subscribe. And we'll see you next month with a new edition of the Heat Treat Podcast with other power players of the industry. I'd like to remind you, we're on YouTube, Spotify, LinkedIn, right? So follow us on the Heat Treat Podcast. Thank you, guys.
Thank you so much.
Thank you so much, brothers.